Basically, I'm introducing myself because they left me here. Uh, so, uh, I'd like to close this conference. I'm very glad that I have the opportunity to. Talking about a very light topic as monad transformers. So I know it's not a perfect timing, and so bear with me. As you know, this is a fill-in for a speaker that couldn't come, so I prepared my slide yesterday night. So they probably don't type check. Most of them do, but not all of them. So be nice, please. So this is me on my way to Venice. And a couple of words about myself. A few things that I do. Some of you know me, I work at Dildo, a company that I co-founded. We do consulting in the least possible boring way. We use Scala a lot, we use JavaScript a lot, with React.js. We try to do things in a functional way. Okay, I would never learn to use this, okay? Warn me if you cannot hear. And other things that I do related to the Scala world, I run the meetup in Milan, the Milano Scala group. Some of you come from there, so you know that. And if you're from Milan and you don't know that, bad, come to our meetings. We're talking about Shapeless in 10 days from now. And of course, Scala-italy. You're here. I'm a co-organizer of this conference, which is a terrible idea because speaking and talking, organizing and speaking is not a good idea. The last person I've seen doing that was John Pretty at Scala World. He was the organizer and a speaker, and this was him after the talk. So I'm probably going to be much worse than that, but I think I hope I can pull up a good talk. So I'd like to start from a question, and it's not a very philosophical question, but it's a Stack Overflow question. I spend a lot of time on Stack Overflow because I don't like to work. And so the question, I'm not going to read through all of that, but the question essentially was this. Can we do better than this, basically? So we have a future of a list of an integer, and the guy was asking, okay, it's kind of awkward that I need to map over the future to get the list and then map over the list. Can we do something better than that? So the core problem there is that we have two maps and one function. We really want to just do one thing, and we need to double unwrap the future and then unwrap the list and then do the mapping operation that we really want. So can we do any better? And first answer that came in was no, it's okay, you just need to indent it. And probably Olaf would be okay with that. I don't know, you just use scala-fmt and do that. Which, by the way, in the specific example, it's fine. It's a very simple example. You don't need to make it overcomplicated. And of course, but we're on Stack Overflow, so I did make it overcomplicated. So I used some science because it works. And so if you consider the theory, because this is the theory, it's not implemented like this in actual Scala collections, the fact that you have a map operation on something, it's a good hint that that something implements a functor. Has a functor defined on it. I'm not going to go into specifics of functors or laws. There's plenty of talks about it. I'm just going to scratch the surface here. But the idea is that if you have a map, it's probably a functor. And again, future has a map because actually implements an instance of a functor, and list the same thing. So if you know a little bit of theory, you know that functors compose. So what you actually have in hands is a future of a list, which is a composition of list with future. So you can compose them. So you do this, basically. I can do the replay, this. You're merging them, right? And this is actually, that's not really good syntax. Like it doesn't really compile if you do that. But the idea is this one, right? So you have a functor of a future of a list. And then if you need to map over a future of a list, you can just use the map function from that functor instead of using the map operation from the first functor, then using the operation from the second functor and doing them together. So squashing them together, okay? In practice, you can do this and with a very simple syntax, and this is the fourth line here. And which is the only line that it's interesting in this slide. I just wanted to put in an example that you can copy and paste, and these type checks and works. You can do functor of future, compose functor of list, and then you just use it. And it's a single map. So we solved that specific problem for mapping over a future of a list of a something. And for doing this, I'm using cats. You've seen it a few times today in other talks. You can use scala-z, which is a similar library. They're basically one the reboot of the other. There's a lot of political stuff that I don't want to get involved into. I like this a little bit better, but I mostly use scala-z in production. So I'm going to point out the differences between the two in the examples, but they're essentially the same for the sake of this talk. So you're not always so lucky that when you map over something, you get, I don't know, you're mapping an integer to a string. Sometimes you're doing something more complicated than that. Like not very complicated. So in the first case, we're good, right? In the second case, we're mapping over a list, and we're returning a list. So it's a list of lists, which typically you don't want. You want a list in the end. So what you do, well, you take a list, you map over it, you return another list, and then you flatten, right? So you're basically composing the flatten operation with the map operation. So you're doing map, and then you're doing flatten. And that works because if you have a list of a list, flatten operation would just flatten the whole thing and give you a list back. Okay? So somebody noticed this pattern, and ta-da, we have flat map. Flat map is the composition of flatten and map. If you come from another language, you may hear this as join a map equals bind. For instance, that's like that in Haskell, if I'm not mistaken. But it's essentially the same thing, is the composition of those two operations. And that loosely relates to the concept of a monad. As before, this is very imprecise, but if something has a map, it's probably a functor. There's so many things that are wrong in this specific sentence, but bear with me. And a flat map indicates that that thing probably implements the instance of a monad. So you have this parallelism between map and functors and flat map and monads, okay? And this is baked into the language, as we will see. So it's important that you understand that these two examples are the same. I think it's fairly trivial, but if there's something that is not clear at this point, please let me know. So in other words, if you have an f of an a, if Leibniz gives you that, you probably want it to flat map. If you have a future of an int, it's a little bit weird, and you probably wanted a future of an int, and you just needed a flat map instead of a map. That's a rule of thumb, let's say. It's not always like that, but it kind of works most of the cases. So let's look at the less contrived example, a little bit less contrived. So suppose you have a function getUser that returns a future of a user, and then you have a function which is our friends, that it's just a Boolean function. It just takes two friends and tells you whether they're two users and tells you whether they're friends. So you could write it like this: it's getUser, flat map. Why flat map? Because the operations inside the returns another future, so you don't want to do the double nesting. And the last one can just be a map because it doesn't return a future, it returns a value, so you're in the first case of the slide that we've seen before. So again, this is so core in doing functional programming that most languages that actually take this seriously have special syntax for that. Whether it's a good thing, I don't know, but I like it. So in Haskell, in Scala, you have something similar. In Haskell, you have do expressions. Here, you have for comprehensions. They're mostly the same. It's the same intuition. We're going to use flat map a lot and monadic comprehensions a lot, so we want a special syntax for that. So again, this example here is the exact same thing as this example here, okay? Just a different syntax. So from now on, I'm going to use mostly for comprehensions. So again, stop me at any time if you don't understand that, because it's just a syntactic transformation and makes the slides prettier. And it's also kind of the kind of code you want to maintain instead of a bunch of nested flat maps. So we learned a couple of lessons. Like monads basically allow you to do this sequential execution. Like you do get that user, then get the other user, then do something with both. And that's why they're powerful, and also that's why they cause problems, because powerful things cause problems. And we wouldn't have monad transformers if monads were easy. And monads basically can squash f of an a into an f of a. Basically, the flat map operation is what it does. It prevents you from having a lot of nested structures, but it allows you to nest. Basically, do a flat map, then a flat map, then a flat map. But the end result, it's always a nice flattened out f. Questions so far? liars. I'm barely with me. You cannot be with me. Okay. Um, so wait a second. Okay, it seems nice so far, and it's always nice when you see easy examples. But at some certain point, you will get this eventually in some form, and I'm going to show you some examples right now. You don't have an f of an f of an x. You can just flat map and you're done. You probably have an f of something else with f and g are different of an x. And so back to the real world, that future user function, it's a lie. If you want to model the fact that the future can fail because the database failed in some way, and also the fact that the user may not be there because the name doesn't correspond to a user in the database, for instance, you probably want to do something like this. It doesn't have to be like this, but usually you may hit this case. And that's the first case that I hit when I was facing with this problem. It was the specific example of having a future of an option of something. So now get user returns an option of something. But you still want to operate with users. So you get this, and you would like to do that, but you cannot. And the reason is that the little arrow, if you remember, basically it's a flat map. And flat maps on a future returns the inside, but the inside is an option. So you cannot just pass the two Gab and Joe variables to the our friends functions because they doesn't type check, because it takes a user, it takes two users, and you have two options of users. You cannot do that. And this is typically when beginners get stuck, because what do? You do something weird. Right? You have to ship this code in production, so you just do this, right? And it works beautifully. I mean, you just get. Why there is even a get in the library? Yay! Done, shipped, production, it works, it's type safe, right? And then you get an exception, and you get basically, your boss says, well, I thought Scala was type safe. Yes, if you don't use a get. So you can do something other than that. You can do, I didn't even know you could do this. I hope you don't do that. This actually type checks and works, and why? You basically, so what's the point? The arrow strips away the future, so do it again and strips away the option. This is a very simple example, and it's already getting complicated, and I don't even know how to parse that. I just know it works. So down, no, it's not really good. Oh, you can do this, so you can do many other hackeries, and it's not good. But you're kind of stuck, right? Because it's nested. You cannot do anything about it. A flat map doesn't help you because you have two different monads there. It's a future and it's an option, so what do? So you say, haha, but it's the same trick as before, right? I have a flat map, which is essentially saying I have a monad of a future and then a flat map over it. Then I have a monad of an option and a flat map over it. How about I compose them, right? Ta-da, and it's n. That's it, and nope, sorry. You cannot do that, and the reason why you cannot do that is basically the core of the mystery of these things that I don't understand, like category theory and those kind of things. Basically, in my personal view, you cannot do that because monads allow you to change the structure of what you've been passed in. Okay, if you map over a list, you get a list back, and the list has the same number of elements. If you flat map over a list, you can do whatever, and that's the power of a monad. You can just return a list which is longer, empty, whatever. You return another list. You have full control, and that's why you use it for sequential operations and for control flow. But that also prevents you from composing them freely, and that's the trade-off, right? Monads are powerful, but you cannot compose them freely, and that's what we're talking about. So monads do not compose. You may hear this a lot, and this is a mandatory link to the Tony Morris blog post. Tony Morris is the original author of scala-italy, which is one of the libraries I mentioned before. This is a great article that it's probably like a very short article. It takes 7 to 10 days to understand some of it. It basically it tells you, okay, try to implement the composition of a functor, easy. Try to implement the composition of a monad. It tries to do that, and it fails miserably. And just the type signature of that article are amazing. So what can we do? I mean, Tony Morris says that monads do not compose, so let's go home and just double yield or yield a match or do something weird. But if we stop for a second and think about this. What's really the impossible part in composing monads? So the point is, the first row, it's really trivial. It's literally few characters of code to do with any library. It's baked in any library. Anybody could write it as soon as you grasp what a functor is. It's really easy. You do the map, and then you do the other map. It's what you would do if you didn't know that functors can compose. The second layer is impossible, which is reminds me of the comic that Andrea and Emanuele showed before. It's like, okay, can you do that? Sure. Can you do that? No, I need a team of experts for, I don't know, 20 years of research and development. This is just impossible in theory, which is saves time. You don't even have to try. So what is impossible? It's impossible to just say, okay, I can get to the monad of Mn just by the virtue that M is a monad and N is a monad. Okay? Try that again. The first function works because f is a functor, g is a functor, and that's all you have to know to provide the functor of f and g. That's it. That's all you have to know. With the monad, that's not enough. You cannot just compose generically to monads because the semantic of a monad, it's so arbitrary, and depending on what the monad is, they can change the structure. You need to know what monad you're talking about. And we will see that in a second. So monads do not compose generically. You cannot just write a function that composes two monads. That's impossible. But you can compose them specifically. And you were already doing that. Any of the examples that I've shown before, they are composing monads in their own hacky way. I mean, even get, it's a composition in a way. You're doing that. You're already doing that in your code. The point is just doing that in a sufficiently generic way that it's not tedious to maintain and write. So let's try an approach and see how it goes. So we can define a case class. We call it FUT_opt. It represents a future of an option. I just didn't want to type the whole thing all the time. And it wouldn't feel as light later. And the FUT_opt just wraps a future of an option. So what's the intuition here? We want basically to do a flat map over future of an option together. So we have a future of an option and we want to flat map over it. But we cannot just do as we did with the functor, just composing the two monads together and then use a flat map operation from that. But nothing prevents us from wrapping it in an arbitrary data structure that we put in, like future of option, FUT_opt, and then implement a monad type class, the monad type class, and just provide our own implementation of a monad, which is not so complicated actually. It's the same code you will write to compose them manually. You just stuff it in a specific piece of code that you reuse. So this is the full definition of the instance of a model for FUT_opt in cats. In scala-z, you probably just change some names, like pure is point. I think that's it. Value is run, but it's essentially the same thing. And it's very easy. And I'm not going to go through this because, well, that's boring. But you can define an instance of a model for the specific combination of a future and an option. And then you can just use it. You can use it like that. Now, the getUser function, which returns a future of an option, you wrap it in a future of option, FUT_opt. And that has a flat map that returns you the user, if there is, for how you implementing it. So you just get it and use it. And that returns the future FUT_opt boolean, which is not what you wanted to, but you can just do f.value. And if you remember, that comes from the fact that we called that value. Okay, so we're just taking it out. We put it in, define a flat map over it, do whatever we want, and we take it out. Okay? All with me? No? Yes? Okay. So what if we have something else, like a list of an option of options, right? It's the same thing. List is has an instance of a monad, the option does, so we want to compose them together. We cannot do that generically, so we do the same thing, same approach. List of opt has a value, which is a list of option. We define a type class for it. We implement the monad, we implement our own flat map, and then we just use it. So if you take a look at this and take a look at this, it's something similar, isn't it? Okay. So this intuition tells us that that's a pattern there, and that's the first monad transformer that we're gonna meet. It's option T. So it turns out that you just need for a monad transformer is just another monad that takes the innermost of the two monads that you're trying to compose and just tells you, okay, I'm an option of T. I can compose with anything that wraps me that it's a monad itself. And actually, in the specific implementation of libraries, if you just want the map of the composition, you can just provide a functor. You don't need to provide a monad. But for the sake of simplicity, F needs to be a monad, and that's it. So you can use it for list, you can use it for future, you can use it for whatever you want. It's a little bit mind-bending, the fact that you're using, basically you're defining the innermost. So if you have a future of an option of something, or a list of an option of something, you use the same thing, which is option T of something is the innermost. And the innermost, which is the one next to the value, the one that's holding the value, option is holding the value that we want, can be wrapped with anything that it's a monad, and we just carry it with us. We add a type parameter, and we memorize what's wrapping us, and we pretend it's not there. So, same example as before. Is like the fut opt example, and it's just using option T from cat or from scala-z. This example works the same in both libraries. So you just wrap option T, get user returns a future of option, and you use it. And then you get an option T of future of Boolean back, and if you just want the future of option of Boolean, which is the result you want, and initially you just call .value on it. Okay, it's the same thing that I did by hand before, and is basically in the library. You can just go and use it, which is great. I mean, this will get you a lot of points on Stack Overflow if you write something like this. I mean, there's good questions that I answered like this. Simplest example are really, really fun. Let's take another example, though, and that's where monad transformers start to get a little bit clunky. Sorry, this doesn't have a happy ending. It's not like monad transformer are really, really the solution to everything. There's many, many problems with those. And another example is if you want to compute a stupid nickname, like my own, you get the user, you get the age, and then you get its nickname, and then you put it together with the age, let's say. So you want to take my nickname, which is Gabriele, my age, which is 27, you compose it together, and you get Gabriele 27. So the first function returns an option of an int, okay, which is good. We can know how to deal with that. But the second function returns a future of an int, and the third function returns an option of a string. So there's something a little bit different than the other ones, right? So you say, oh, I know the trick. I just use option T for everything and just gets wrapped into this nice thing that apparently solves my problem, and I use it. But it doesn't work. It doesn't work because option T works specifically with something like f of option of something. Okay, you need to have that shape. You want that shape. And in the second case and in the third case, you don't have that shape. You miss the option in the get age, just returns a future of int, and you miss the future in the other case. You want the a future. It's an option of string, and you want a future of an option of something. So that doesn't work. And that's where things get like that. You need to make it fit in that shape, and that's why monad transformers get complicated after a while. And so this is in cat. There's similar methods in scala-z. I need to give credits to Alessandro, who implemented the liftf in cat, and thank you for that. That's very convenient. So basically, you have few methods that I don't want to get into details about, but they basically cover a few basic cases that you might encounter, like the ones I showed you before. Like if you have a future of A, but you're working with a monad transformer that it's a future of option of something, you can lift it. Basically, you wrap an option around the innermost value and go with it. Or if you have a simple option, you can just do from option. That's a lot of work that you need to do manually. You basically have a nice shape you can work with, and you just need to get there manually. There's other ways you can just wrap get name in a future. You cannot use the libraries for that. You can do it by hand, but it's a little bit clunky after a while. So let's go with another example. It's basically it's a stripped example from our code base. And it's about updating a user. So you need to, for updating a user in the database in this specific web application, you need to check whether a user exists. you need to check whether it can be updated according to some validation logic, and then you update it. So the first time you model this, if you're just new to Scala and you just model this without thinking too much, you just say, okay, checking if a user exists is a future of an option of user, because it's async and it might not be there. Checking that can be updated is a future of Boolean, for simplicity, like, okay, just true or false eventually, because I need to check something else on the database. And updating the user on the database is a future of user. It just you update it and you return back the successful updated user. And if you try to use it, this is the first example in which I don't use for comprehensions because it's not simpler than this. You basically need to flat map over the first operation, then you do a lot of basically heavy lifting because you have a maybe user back, and then you map over it. It's the same problem as we've seen before, right? You need to specifically deal with the fact that you have intermediate data structure that you don't really care about. If it's a future of an option, I just care if the user is there. Eventually, and it might not be there, I get it, but if the user is there, I want to do something with it, otherwise not. And this doesn't, it's really in your face, what you're doing, and it's hard to maintain. You need to pick the right names, it's bad. I had a really hard time writing this code. More problems arise if you want to return, let's say, not like, okay, if something goes wrong, I return none. No, maybe I want to be more specific and return something like an error. Like for simplicity here, the error is a string. And here I'm using a data structure, which is XOR-T, which we've seen in the Clements talk. And it's basically either from scala-z, the sort of V, which is disjunction. And so that in this case, my return type of the future is either an error, which in this case is basically a wrapper around the string, or a user. And in this case, it gets even more complicated because I need to like scatter around all this code. Of course, you can refactor it to make it a little bit better, but the core problem doesn't really get solved. And so, of course, XOR has a transformer, right? Because it's a model, you can compose it. And there's a specific transformer for XOR that we use it. We use the scala-z version, but I like to show that it's basically the same in this other library. And it works like this. This is what we did after the first making mistakes in the first case. So we have an error type. It can be like a tree of types of errors, but in this case, it's just a wrapper around the string. And then you have a result type, which is you provide a type alias, so you basically fixate the error. So the error is going to be that type, and then you have a generic result type. And that's nice because if you deal with Scala, there is a famous and infamous SI2712, which is a bug in Scala in the type unificator. So it's better if you have just one type parameter, trust me. Then we define basically an alias for that transformer, in which we say, okay, result T, the transformer, is the transformer of XOR T where I've just fixated the error. So this can represent a computation that maybe it's a future of something and has a specific error type. So is this like option T if you look at it? Okay, there's no difference between a result T and option T from the user point of view, except that you need to take care of returning that specific error and not a none, for instance. And then you can define something like future result of A, in which you fixate also the F that wraps around, and it's a future. So a possible approach to make your code better is to just choose a shape, which in this case is basically a composition of effects that you know you're going to have, like asynchronicity, like future. Duality, you can have either an error or a value, and you just do, you pick a data type. In this case is future result of A, and you just use it in your methods. And again, this is opinionated, and I don't even have a strong opinion about this, but you could do this, which is the check user exists function. Instead of returning a future of option of user, and then you return a future of int in another case, you just make all of them return the same thing, the future result of user, which means you're scattering the heavy lifting of wrapping and lifting things into that specific shape across several methods. But it's a little bit nicer to read, and then it's nicer to compose, because here you just say, okay, that's my stupid validation thing. Okay, it exists if the ID is 1, 2, 3. And then I just return that dot right just puts it in the XOR monad that we've seen before. And you do similar things with the others, and it's a little bit better, right? You can just call them and you compose them as you want, and you get a future result of user. In our specific code base, we even take that and serialize directly, so we never run value on it, like explicitly in the code. We just take it and serialize it back to Spray. And that's it. I don't sound really enthusiastic, and because I'm not about this, there's a lot of lifting required in the methods. And well, I would like to explore a little bit better these things, and if someone does it differently, I think it's better, please come talk to me. I'm very glad to have a conversation about this. But I've used it for a while, so I have some tips about it. So stacking 2 monads is kind of okay. Stacking more than 2, it's daunting. It's really, really, really complicated very quickly. So this is an example from M, which I'm gonna mention later. This is just stacking 3 monads. In this case, it's an option of an either of a it's a task of an either of an option. It's a task from Scala that it's like that, because you need basically to lift everything inside the right thing. You do basically placing every shape in the correct container, and then you put it together, which is really not solving the problem. It's not better than doing it by hand, probably. And this is possible anyway. You just need to know that it's possible because, again, as I said before, a transformer is just another monad. So, of course, you can compose it with another transformer. So you can have an option of T or list of T of something. But in the end, it's really, really complicated to use. And second tip, keep your transformers for yourself, in the sense that if you're exposing a public API, you probably don't want to rely on a specific implementation of transformers. Even in internal code, sometimes be careful when you expose that. If you're exposing that at the boundaries of something that is not directly under your control, don't, probably. Because that's, if you want to change the library, you change from Scala-Z to cat, you're basically screwed. And if you're exposing a lot of internal things that you don't want to. Just stick with plain Scala values. So expose a future of an option of an int. It's really easy to get one if you have a transformer. Once you have done all the heavy work of getting that value, you can just call value on it. And in Scala-Z it's run, and you just return the actual value. So please don't expose directly transformers. And consider that doing within your code, be considerate. So some takeaways from monad transformers. They end with T. If you see something T, is probably a transformer. It's basically you have f of g of x that becomes a gt of f of x. So you're basically saying, okay, I really want x, so let me just strip away the wrapping, and I save it in another type parameter that I will apply later. So that's the general idea, the general feeling that you get from those. They can be stacked indefinitely, but nope, it gets really complicated. And they're a tool for stacking effects. They're not the tool for stacking effects. What we're doing here is stacking the various monadic effects, like option, like future, like list. Those are all monadic effects in the lingo. And they're one tool. There's other tools, which I would love to talk to you about, but I know very few, but these are pointers for both you and me, and to have a nice conversation later. So another way of composing monads is free monads. This is probably even more complicated to get, but it's much nicer to write and read. And the basic idea behind a free monad is that you separate the structure and the interpretation. So once you're defining how your data flows, once you're defining the structure of your program, you're not dealing with the fact that that code runs inside a specific effect. Like you're not dealing with the fact that that specific value is asynchronous, it can be optional, etc. You just define the flow and then you interpret it. So you still have the problem, but they're not entangled together. You're not mixing the fact that you have to define what the program does and you have to run it. So there's a really nice introduction to free monad, by the way, which is understandable, which is good for these kind of topics, which is in type level CAT's library itself. CAT provides an instance of the implementation of a free monad, and there's a nice README that I really suggest you to read. It's very, very to the ground, and then he builds up specific concept that you get abstract in the end, and it provides all the information you need, but it starts from very basic examples, which is really nice. Another thing that is going around for a while, it's the F monad, and F is based on Oleg Kizelyov, I don't know how to read that, Oleg's paper, which is basically based on the concept of free monad and allows it to compose effect in a more predictable and easy way to at least maintain. But it does a lot more than monad transformers. It's very much more. It does very other things that you cannot do with just a monad transformer. And on the other side, there's an implementation in Scala made by, I think it's maintained by Eric Torrebore, and it's FCAT. There's one for Scala Z too. Another thing that I've been experimenting a little bit with, it's M, which is the same thing, but easier, in the sense that it doesn't want to add things to monad transformers. It's just an alternative. It's basically a stripped off version of F, which does a lot of things more than you actually may need. And it's from Daniel Spivak. And I recommend that you read the README because it gives you the example of a complicated monad transformer that I've taken is from this README. And it opens your eyes on what you can actually do. Like the example that I showed before is much easier with this specific implementation. Of course, there are trade-offs. There's no free lunch, but it's a researching topic. So I'm basically done. I mean, the purpose of this talk was not to advocate monad transformers, as you may have noticed. I just wanted to let you know what they are, which kind of specific problem they solve, and when you face the specific problem, consider using them. Try experimenting with them and see whether they facilitate your life. Because in the end, I keep saying that they're clunky, that I don't like them, but it's much better than we had before. So it made our code base better, and I think it can do the same to yours. And then experiment with other things. There's M, there's the free monad. Just find something that suits your needs. And if you find something better than what I just told you, please come to me and talk. And speaking of which, if you are the Slack kind of guy, we have this Slack at scala-italy.it. If you want to join the conversation, we are there mostly saying stupid things, but sometimes a nice conversations come up. And we need more people to talk with. So we're kind of 100 people right now, but all of you are welcome. And if you want to work on these things, well, you may work with me. So if you're interested in working in solving these kind of problems, just mail a CV there. That's what I got. Thank you. Questions? Or just leave and be free? Second option, I think. Okay. Thank you very much. Thank you very much for coming to the conference. I mean, that's the end of it. I hope I see you again next year. Thank you all.